Ramil, maybe we can start our lecture now. Participants and our students, maybe yeah. Attend. Yeah. I will greet Mr. Dr. Ramil.
Okay, so good morning, everyone.
Morning.
Morning.
Maybe the first I will read the agenda, Mr. or Doctor. I will share my screen and I maybe greet in our class. We have Mr. Jun Bodales from I said you, yeah, Iloilo Science and Technology University. Maybe you can greet us, Mr. Jun Bodales. And we have Mrs. Nimia. Maybe you can greet us in this class. Yeah, I will say thanks for from Philippines. Yeah, Iloilo Science and Technology University for the attend, and maybe I will share the agenda for now. Yeah. Maybe we has see that Iloilo Science and Technology and Bina Insani University guest lecturer and list of the activities and agenda for the first opening and playing, and second forward from Bina Insani University, and third presentation from Dr. Ramil, four question and answers, five conclusion, and six closure. For the first agenda, we will open our lectures and praying together. Take our time in maybe 1 minute for praying. Let's pray, begin. Praying is the end, and the next agenda is maybe forward from Bina Insani. That is maybe is me. Yeah, I will say warm greeting from Indonesia to Philippines. Good morning, selamat pagi. Maybe first I'll say thank God Almighty for giving help to all of us to be able to attend these lectures. And second, I will say thank you very much to Dr. Ramil because he was prepared to spend his time as a guest lecturer at Bina Insani at these lectures. And as I will say thank to Iloilo University. Maybe this in this class we have Mrs. Nimia, we have Mr. June. Yeah, thank you for attend in this lectures, and we believe that the experience expertise of Dr. Ramil on the above mentioned topic would help faculty of informatics Bina Insani University attend its objective of giving a more meaningful, yeah, significant and impactful learn experience to its students amid this pandemic. And I apologize if there were mistakes during preparation and during lectures, especially in my lack of speaking English, because it's everything we use bahasa, yeah, not English language, doctor. That's all I can say, and thank you infinitely to Dr. Ramil. And the next event or agenda is presentation from Dr. Ramil about the topic is pipelining on architecture and computer organization. To Dr. Ramil, maybe take your time to presentation. Thank you.
Okay, so good morning once again. Can you?
Good morning, Mr.
Okay, so let me share my screen first. Okay, so can you see my screen now?
Yes.
Yes, sir.
Okay. So again, good morning, and thank you very much for inviting me as your guest lecturer for this topic, pipelining on architecture and computer organization. Ari have messaged me last night that you have already learned some topics pertaining to the basics of computer organization. So that is why I will have to center my lecture on pipelining topic, since most of the basic parts of computer operations, you learned that one already. So in here, we'll focus on the pipelining topic, in which how this instruction set is implemented inside our computer system. But before I begin, so let me first share to you this video.
Sorry, doctor. The sound is very.
Hello, sir.
Yeah.
Let's imagine that we can shrink
Ah,
the
yes.
size of an electron and inject
And
ourselves
because the requirement here in
If you
PLC
took your mouse
stage
apart, you'd see that
is
it's
not
Sir
enough
Ramel, mahina ang audio, Sir Ramel.
it has a couple.
actually when
Yes, sir.
Mahina ang audio, sir, sang imo nga video nga gina-present.
stakeholders
Wait. Naka-live on siya sa YouTube.
and so
Okay, wait lang.
and then you go back to
Maybe you can share sound too in share screen. Yes. Or you can close.
Yes, for a while.
So, re-share. Maybe you can close first and share sound. Checklist share sound on share screen.
Wait for a while. I'll check the audio.
Sir, you have mag-share ka, sir, may ara sa sir nga checkbox nga share sound.
so what
I-click
is
mo siguro, sir, ang share sound.
Scrum
Sa share screen.
Ha, sir, sa share screen, tapos may share sound sa nga makita ka.
Maybe I will stop
wait.
your
Okay.
participant sharing and re-share again.
Okay. So I got it already.
Nah,
Okay.
before you share screen, you can checklist share sound too. Yes, we have already.
Do you remember when you first realized that your computer was more than just a monitor and keyboard? That between the mouse click and the video playing, there was something that captured your attention, understood it, and made it real? What is that something? Is it gremlins? Let's imagine that we can shrink down to the size of an electron and inject ourselves into a click of a mouse. If you took your mouse apart, you'd see that it's really a very simple machine. It has a couple buttons and a system for detecting motion and distance. You might have an optical mouse that makes these measurements with lights and sensors, but older ones did this with a hard rubber ball and some plastic wheels. Same concept. When you click the button on your mouse, it sends a message to the computer with information about its position. When your mouse click is received, it's handled by the basic input-output subsystem. This subsystem acts like the eyes and ears and mouth and hands of the computer. Basically, it provides a way for the computer to interact with its environment. But it also acts like a buffer to keep the CPU from being overwhelmed by distractions. In this case, the I/O subsystem decides that your mouse click is pretty important, so it generates an interrupt to the CPU. Hey CPU, got a click here. The CPU, or central processing unit, is the brains of the whole computer. Just like your brain doesn't take up your whole body, the CPU doesn't take up the whole computer, but it runs the show all the same. And the CPU's job, its whole job, is fetching instructions from memory and executing them. So while you're typing, maybe really fast, like 60 words a minute, the CPU is fetching and executing billions of instructions a second. Yes, billions, every second. Instructions to move your mouse around on the screen, to run that clock widget on your desktop, play your internet radio, manage the files you're editing on the hard drive, and much, much more. Your computer's CPU is one heck of a multitasker. But oh my gosh, there's a very important mouse click coming through now. Let's drop everything now and deal with that. There are programs for everything that the CPU does. A special program for the mouse, for the clock widget, for the internet radio, and for dealing with letters sent by the keyboard. Each program was initially written by a human in a human-readable programming language like Java, C++, or Python. But human programs take up a lot of space and contain a lot of unnecessary information to a computer, so they're compiled and made smaller and stored in bits of ones and zeros in memory. The CPU realizes that it needs instructions for how to deal with this mouse click, so it looks up the address for the mouse program and sends a request to the memory subsystem for instructions stored there. Each instruction in the mouse device driver is duly fetched and executed. And that's not nearly the end of the story. Because the CPU learns that the mouse was clicked when the cursor was over a picture of a button on the monitor screen, and so the CPU asks memory for the monitor program to find out what that button is. And then the CPU has to ask memory for the program for the button, which means that the CPU needs the monitor program again to show the video associated with the button, and so it goes. And let's just say that there are a lot of programs involved before you even see the button on the screen light up when you clicked it. So just the simple task of clicking your mouse means visiting all of the critical components of your computer's architecture. Peripherals, the basic input-output system, the CPU, programs, and memory, and not one gremlin.
Okay, so that is a simple way of illustrating how the computer system works, and I believe that we really understand now, we already understand how this basic computer architecture and organization works. So for today's topic, so we'll have first a short review of the architecture and organization of the computer. Then we'll be talking more of structure and function, instruction set, then the highlight of our topic, which is pipelining, a design of a basic pipeline, pipeline dependencies, data hazards, solution for pipeline dependencies, pipeline development, and of course, sum up the topic now for today's lecture. All right, so organization and architecture. No? So there are two ways to describe our computer system. No? So it is based on its architecture and organization. So when we say computer architecture, it refers to those attributes of a system visible to a programmer, or put another way, those attributes that have a direct impact on the logical execution of the program. So the architecture refers on the logical application of the program, which focus on instructions, programming, coding. No? So this type of application is under the computer architecture. Then for computer organization, it refers, of course, to the operational units, their interconnection that realize the architecture specification. So computer organization focus more on the physical aspect of the computer, while the architecture refers to the logical aspect of the computer system. So example of a computer architecture attributes includes the numbers of bits to represent in various data types, numbers, characters, input-output mechanism, and memory addressing. So while the example of organization attributes includes the hardware details, such as control signals, interfaces, computers, peripherals, and the memory. Okay, so those are an example of computer organization. So for the structure and function, so structure refers to the way in which the components are interrelated. So in here, it composed of the different interrelated components, such as the central processing unit, which controls the operation of the computer and performs its data processing function. Then we have the main memory, of course, that stores the data, the input-output, which moves the data between the computer and its external environment, and the system interconnection, which provides mechanism for communicating between the CPU, the memory, and the input-output operation. For the function, so it refers to the operation of each individual component as a part of the structure. So there are four main functions of the computer. So it includes the data processing, the data storage, the data movement, and the data control, wherein it provides, of course, in the operating environment of our computer system, as illustrated in this picture. So what are the example of the logical way of representing the computer is through the form of instruction set. So of course, as we have seen in the video presentation, the moment we issue a command or an instruction, that is where our computer system follows those specific tasks based on the instruction issued by the user. So it is called an instruction set. So an instruction set is also called instruction set architecture. It's a part of computer that pertains to programming, which more or less the machine level language that can be understood by our computer system. Then the instruction set provides commands to the processor to tell it what it needs to do. So of course, after the instruction is set is a way of telling our computer to perform something. Then the instruction set consists of addressing modes, instructions, data types, registers, memory architecture, interrupt, and exception handling, and the external input-output operation. So this makes the whole instruction set architecture. So examples of instruction sets. So for example, if we are performing programming or basic operations, so we have adding two numbers, comparing two numbers, input from a specific device, for example, a keyboard, a mouse, or any input operation. Jump to the designated RAM address. Jump if conditional statement. This is, for example, if we are doing programming that have a branching or sequential operation. And then the load of information from RAM to the CPU. Out, this is for the output operation. Let's say, for example, displaying an output to a monitor, to a printer, or to any output devices. And then store information to the RAM. So these are all the basic examples of instruction set wherein these instructions are used to initiate a command that will be performed by our computer system. So the central processing units is, of course, that is the main component of our computer system wherein it does the processing of all the tasks. So in order for it to be more efficient, our computer system must have a better performance in order to perform all the specific tasks. So the performance, the efficiency and the output of the task depends on the performance of our central processing units. So there are two ways to improve the performance of the CPU. First, improve the hardware by introducing faster circuits, or arrange the hardware such that more than one operation can be performed at the same time. But however, the first option is much more higher in terms of specification. It's much more expensive since this is improving the hardware part of our computer system. So this is more expensive in terms of building our computer architecture. And there is a limit on the speed of the hardware and especially the cost of the circuits, which is very high. So currently, modern computer systems are into the second options wherein they arrange the hardware that one of the operations can be performed at the same time now. So which is, of course, improving the performance by arranging the hardware to perform better. So this is the concept of pipelining, all right? So pipelining is the process of arrangement of hardware elements of the CPU such that its overall performance is increased. So in order to increase the performance, so a specific arrangement were done, and it is in the form of a pipelining. So in order to provide a simultaneous execution of one or more instructions that takes place in a pipelined operator. So currently, our modern computer are capable of handling multitasking applications. It can perform one or more tasks at a time. So that is why this concept of pipeline makes it our computer to execute one or more instructions simultaneously to make it to have it a overall performance. So how does pipelining work? So let's have an example in here. So let us see in real example that works on the concept of pipeline operation. Example, consider a water bottle packaging plant. So assuming that we have a bottle packaging plant and there are three stages in producing that one. So the first stage is inserting the bottle, that is I, inserting the bottle I. So once the bottle is inserted, so we have to fill it with water. And lastly, seal the bottle. So that is three stages. So each stage, let's say for example, takes 1 minute to complete the operation. So we have to simulate this one. No? So in a non-pipelined operation, so when we say non-pipelined, the instruction is done sequentially without overlapping. So for example, in a non-pipelined operation, so during the first stage, so the bottle of the water bottle is inserted. So after inserting that one, so it moves to the, after 1 minute, it moves to the second stage wherein we fill water out of that bottle. Then after filling the bottle, so we go to the next stage, the last stage, which is the packaging. All right. So from stage one, so inserting the bottle, go to the second stage, filling of water, and last stage is packaging, which is we already completed the operation. So in here, so without pipelining, so each operation, since it is done sequentially, so the two operations in here have to wait to finish this production in order to produce another one. So it takes 3 minutes to finish this one. So since each of this operation is 3 minutes, so the three operations is 9 divided by 3. So the total operation is 3 minutes. Okay, so what we have noticed in here that while it is in the second or the third phase, so there are no other operations performed on these stages. So again, in a non-pipelined operation, we need to finish a specific operation to execute, and then we go back to another application. So for a pipelined operation, so let us see how it is done. So for the first stage, we insert the bottle, and then when we go to another stage, when we fill up the water, we have to insert again another bottle in here. All right, so take note, there are no stages left unprocessed. And then once this bottle is forwarded to the third stage for packaging, this bottle will be filled again, and we have to insert another bottle in here. So it performs a multitasking application in using the pipeline operation. So in here, the overall time spent now for every battle and every stages is only 1.67 minutes as compared to 3 minutes without the pipeline operation. So in short, pipelining lets us process instruction in a parallel and simultaneous format, improving the speed of the operation. And that is how our modern computer architecture is doing right now in our central processing unit in order to provide a better performance and speed up the operation process. So in an unpipelined processor, so these tasks are done sequentially in just one clock cycle. So in short, in a one clock cycle, we need to finish this one. So let's say fetch an instruction, decode, read, perform, write. But however, each instruction need to execute completely, and we cannot execute another instruction unless this whole operation is executed in a one clock cycle. So in designing a basic pipeline, in a pipeline processor, so a pipeline has two ends, the input end and the output. So between these ends, there are multiple stages or segments such that one stage is connected to the other stages in a specific operation. And then it also includes the interface or registers that are used to hold the immediate output between two stages. And these interfaces of registers are also called the latch or buffer. So all the stages in the pipeline along with the interface register are controlled by a common clock. So in short, each operation is performed using a one clock cycle. So in designing a basic pipeline, we are also following 5 stages. So stage 1 is the instruction fetch. In this stage, the CPU reads instruction from the address in the memory whose value is present in a program counter. So in here, we have the first stage, fetching an instruction. Then second stage, instruction decode. So instruction is decoded and the register file is accessed to get the values from the register used in the instruction. So followed by the next stage. So stage 3, instruction execute. In this stage, the arithmetic and logical unit operations are performed. Then after that, stage 4 is the memory access. So memory operands are read and written from the memory. And then that is present in the instruction. And the last stage is write back, wherein in this stage, computed or fetched value is written back to the register present in the instruction. So in here, in a one clock cycle. But however, as you can see, these operations can overlap in a one clock cycle. And we have a latch in here now. So the latch is the registers in between these stages wherein we can perform overlapping applications in executing the pipeline operation. So this is an example of the execution of a pipeline processor. So there are 2 ways to execute. We have the non-overlap execution, and then we have also the overlap execution. So in here, for every cycle and every stages, so the instruction is performed, but however, we can see that every cycle, there is no overlapping instruction in here. So it is done sequentially. In an overlap, as you can see in a non-overlap execution, so it consumes a total time of 8 cycles. While if the pipeline is executed in an overlap execution, so how can we determine if the instruction is overlap? So we have here cycle 1, stage 1, and then take a look at in here, cycle 2, stage 2. So instruction 2 and instruction 1 is overlap. Same is to this one, there is an overlapping cycle in here. Same is true with this one. So by overlapping the execution, we can decrease the total time executed by the certain process and reduce it into smaller time. In here, in an overlap execution, it only executes 5 cycles compared to the non-overlap execution, which consumes 8 cycles. So the overlapped execution lessens the cycle time of a specific process. Instruction throughput. So pipelining increases the processor performance by also increasing the instruction throughput. So this is how we increase the output of a specific process. So several instructions overlapped in the pipeline cycle time can be reduced and therefore increasing the rate at which the instructions is executed. Now, so reducing the rate but increasing the output. So that is how our pipeline operation works. However, there are limiting factors. Now, there are limiting factors or some issues pertaining to the execution of a pipeline's ability to execute instruction at its peak rate. So these limiting factors are the dependencies. So dependencies between instructions, operands, or we call this one as a data dependency hazard. And then the branches, or called the program flow control hazards, and the time required to access the memory. So these concerns specifically happen in an overlapping pipeline operation, since in an overlapping, instructions are done simultaneously, but however, data, the result of the operation sometimes depends on its previous data. So that is why we call this one as a data dependency hazard. So later on, we'll have an example for that. And then another one is the branching, especially if the program flow is not sequential, if you are using a branching or a loop application, so it might affect the overlapping of the pipeline, since it performs simultaneous operation in a loop or a branching or a selection function, especially if you're doing programming. So data dependencies in a pipeline processor. So there are mainly 3 types of dependencies so possible in a pipeline processor. So first is the structural dependency, the control dependency, and the data dependency. So we will discuss this one by one, how it affects the pipeline operation. So these dependencies may introduce as stalls in the pipeline. So what is a stall? A stall is a cycle in the pipeline without a new input. Let's say, for example, a stall is similar to a delay or a specific event wherein a specific cycle does not process anything or do not have any process at all, and it causes the process to wait. Now, that is an example of a stall, or in a simple way, it is a delay in an operation. So take note, our main target in here is to lessen the time, but increase the output. But however, if there are a lot of delays or stall, it may affect also the producing of our output. So structural dependency, so this dependency arises due to the resource conflict in the pipeline. So resource conflict is a situation when more than one instruction tries to access the same resources in the same cycle. So a resource can be either a register, a memory, or an arithmetic or logical unit. So this is an example of a structural dependency. All right. So if you try to look this one, so the highlighted one under cycle 4, instruction 1 is the memory allocation, wherein in order to execute this one, the output of this one, the output of this one depends on the implementation of this memory. So that is why this process is still dependent on this application. No? So that is what we call the structural dependency. So there is a conflict in terms of resources. So instruction 1 in cycle 4 is using the memory. So take note, this process is overlapping in cycle 4. So there are 4 overlapping process. We have the memory, the execution, the ID, no? And then another one is using the memory also. So in here, there is a conflict of the resources, since both of these instruction 1 and instruction 4 are both using the memory. So there is a conflict in terms of memory resources. Okay. So what are the solution to how are we going to deal with this structural dependency? So the solution for structural dependency. So to minimize structural dependency stalls in the pipeline, we use a hardware mechanism called renaming. So the solution for structural dependency is renaming, wherein we divide the memory into two different modules used to store the instruction and data separately, called the code memory and the data memory respectively. No? So code memory will contain all the instruction, and data memory will contain all the operations that are required for the instruction. So in here, going back to our issue, so the solution in here is to divide this memory, since the two uh, instructions uses the same memory, but however, they have different access to that memory. So what we're going to do is we need to rename this memory and divide this one into two, so that both of them can share either the code or the data. No? So that is the process of renaming. So by renaming, so we can already have here the implementation of the pipelining in an overlapping procedure without resolving resolving the conflict of structural dependency. All right. So currently there are no conflict already of these different resources, because the memory were divided into two. We have the code memory and the data memory. Then another dependency is what we call the control dependencies, or the branch hazard. So this type of dependency occurs during the transfer of control instructions such as branch, call, jump, and etc. So if we are doing programming and uses a lot of branching operation, so it may cause also an issue in a pipeline operation. So many instruction architectures, the processor will not know the target address of these instructions when it needs to insert the new operation into the pipeline. And due to this, unwanted instructions are fed to the pipeline. No? So consider the following sequence of instruction in the program. So we have the codes in here, code 100. So we have the instruction 1. Then the instruction 2 calls for a jump operation, jumping to code 250, wherein it consists of another instruction. No? So take note, the expected output in here is from instruction 1, right? Then going to instruction 2, then jump to the next instruction. No? So this is what we call a branching hazard. So it jumps from one sequence to another. So generally, the target address of the jump instruction is known after the stage only, since in here, during the instruction 2, we have not yet known ahead of time the address of the specific operation wherein it is going to jump. And we only know this ID when the jump operation was already executed. So it may cause sometimes an invalid operation wherein a specific branching will move from a different code. So in here, we have an example. So the output sequence is from instruction 1, all right? So after the instruction 1, it moves to the instruction 2, so calling the jump function. So instead of executing the instruction 3, it moves directly to the next instruction, which is the B1, no? Right? So this is an example of a branch hazard. So a branch hazard is a specific instruction tends to jump from one process to another without knowing the ID of that specific operation. So the output sequence is not equal to the expected output. That means the pipeline is not implemented correctly. So to correct the above problem, we need to stop the instruction fetch until we get the target address of the branch operation. And this can be implemented by reducing the delay slots until we get the target address. So there's a possibility that the pipeline will not be implemented correctly, since it would cause a different address to move. So the solution in here is to reduce the delays. No? So reduce the delays and um, is to introduce a delay so that it will wait for that specific function to return and then execute the operations again. So in here, the output sequence is from instruction 1 to instruction 2. So before we move to this instruction, so we need first to issue a delay in here so that while it is being processed, so there will be no other process to be done until such time that this process will be terminated and then release the delay or the stall to continue the operation. So the solution for control dependency, so branch prediction is the method through which stalls due to control dependency can be eliminated. So in this, at first stage, prediction is done by which the branch will be taken. For branch prediction, branch penalty is 0. So branch penalty is the number of stalls introduced during the branch operations in the pipeline processor and is known as a branch penalty. So in here, the total number of stalls introduced in the pipeline due to branch instruction is equals to branch frequency times branch penalty. So what does it mean? So in a control dependency, sometimes we need to execute what we call a branch prediction. So what we're going to do, we're going to compute the frequency of that specific branch and its penalty. So when you say penalty, it should not have executed a stall. So for example, if a branch has more stalls, therefore it incurs also a lot of penalty. And during the branch prediction, that branch specifically will be terminated in order to release other operations. So it depends on the number of the frequency of the branch and the number of penalty it incurred. And during the branch prediction, all the branches that has more than penalty will be the one to be terminated. So for branch prediction, it looks for a branch penalty that is equal to 0. Okay. So, and then remove all those other branches that has one or more penalty. So in order to resolve the control dependency. Another one is a data dependency hazard. So let's try this example. We have two instructions, instruction 1 and instruction 2. So in instruction 1, we have to add 3 registers. So add register 1, register 2, and register 3. And the second instruction performs a subtraction process which subtracts register 4, register 1, and register 2. But however, try to look at this one. Currently, register 1 is involved in the addition process. So this is what we call a data dependency. So we cannot perform a specific operation until such time that the value of R1 will be updated. So later on, if we try to execute this one without updating the value of this register, it might have the possibility that this will have a wrong value later on. So this is what we call the data dependency. We cannot perform a specific operation since that specific value is still used in another operation. So when the above instructions are executed in a pipeline processors, and then the data dependency occurs, which means that instruction 2 tries to read data, so it tries to read the value before the instruction 1 writes the data in here. So therefore, the instruction 2 might get an incorrect value from this one, all right? So to minimize data dependency stalls in the pipeline, we execute what we call an operand forwarding. No? So this is an example now of a data dependency hazard, all right? So we use this value, we execute this value while it is still being used in another value. So to resolve this one, open forwarding is used. So what is open forwarding? So in operand forwarding, we use the interface registers present between the stages to hold intermediate output so that dependent instruction can access the value from the interface registers directly. So again, consider these two examples. So we add 3 registers. So our register 1 is currently in the add operation, while in here, the subtract process utilized register 1, which is currently in this specific operation. So in an operand forwarding, so what we're going to do is we hold first, right? We hold first the operation of this one and wait until this operation has already been performed and the value of this one has been updated already so that it will be utilized in this next operation. Okay? So there are three types of data hazards. No? So data hazards occurs when instructions that exhibit data dependence modify the data in different stages of a pipeline. So hazard cause delays in the pipeline. So there are three hazards. So again, when we say data hazard or data dependency, the value of the data is dependent on the other operations. So there are three data hazards. So we have the row, or what we call the read after write. Then we have the war, or the write after read. And we have the wow, or the write after write. No? So the row, the flow or the through data is called as a flow or a through data dependency. So in short, we cannot first read a value while it is still being written. So we need to wait first to finish the write operation after we read the specific value. And then this is for the war, or the write after read. This is an anti-data dependency. So we need to read first the value, then after that, write the specific value to update the data. And then output data dependency in here. So write after write, so we cannot yet write a specific value to the output if that specific operation has not been completed yet. Okay. So we'll illustrate the three data hazards in here now. So this is an example of a row hazard. So for example, let there be two instructions, I and J, such that J follow I. So this is what we call a row hazard. Of course, when instruction J tries to read the data before instruction I writes that one. So this is an example of a row hazard. So we have two instruction I and J. So currently, register 2 performs an addition operation of register 1 and register 3. All right? But however, R4 tries to read the value, gets the value of R2 and R3. So in here, a row hazard occurs is because operation G tries to read the data of R2 while the current instruction is still in the writing process. So we cannot do that one. Now, while the operation is in writing process, we cannot yet get its original value. So we have to wait until this write operation has been performed, and then that will be the time that we are going to read the value of that particular register. So it causes what we call a row hazard. Then for the war, so same instruction. So the war occurs when instruction J tries to write data before instruction I reads that one. Okay. So another the same example. So we have instruction I and instruction J. So currently, register 2 is writing data by adding R1 and R3. However, the R3 in here performs an execution by also adding the R4 and I5. So it causes a write after read operation, or the war hazard. So in here, the instruction J tries to write the data, right? So tries to write a data to R3 before these specific instructions performed by R2, wherein R2 uses the value of R3. Okay, so again, in a pipeline operation, we cannot write a specific value while that specific register is still in a read operation. So we cannot write a specific value to a register if that register is currently used and being read by another register. So that is what we call a write after read hazard. Then another one is the data hazard. So we call that one as WOW, or the write after write operation. So it occurs so it occurs when instruction J tries to write output before the instruction I writes it. So for example, another one, we have two instruction I and J. So take note, currently we have two registers R2, which is both writing a value. So instruction J writes a value to R2 by adding R1 and R3, but however, J is also using R2 and writes a value by adding the R register 4 and register 5. So it causes a write after write hazard wherein we cannot write a specific output before a specific instruction writes that one. So what we're going to do is we need to wait first after this write operation, update this value, and then you execute another operation to update again the other value of this one. So we cannot do a simultaneous write execution of the same register in both instructions, and it causes what we call a write after write hazard. So what are the solutions for this data dependency? So again, we have the different solution. Forwarding, so it adds special circuitry to the pipeline that is comprised of wires, switches, with which one forwards or transmits the desired value to a pipeline segments that needs that value for a computation. So this is this is a more expensive solution wherein we have to add special circuitry, wires, switches, or any other hardware components to forward or transmit the value to a specific pipeline for computation. So in short, we need to tweak our hardware and add specific circuitry to add more circuitry and other pipeline stages, no? So to increase the pipeline stages. So another solution is code reordering. So here the compiler reorders statements in the source code, or the assembler reorders object code to place one or more statements between the current instruction and the instruction in which the required operand was computed as a result. So the code reordering will be based now on the design of our source code or our assemblers. No? So in here, we need to redesign the code by reordering the structure in which it can perform a better concurrent instruction. So this is more of programming the specific application in order to resolve the data dependency. Then another one is the stall insertion. No? So it is possible to insert one or more stalls, or what we call this one as the no operation instruction. So when we say no ops or the non-operation instruction, we just simply put a specific instructions where there is non-operations being performed, and it's just a specific delay to momentarily wait for a specific process to perform until such time that the process has already been executed and used that one. So for example, in a write after read process, so we cannot write a specific operation while it is being read by the previous operation. So what we're going to do is, while the operation is currently in a read, by the specific register, we execute first a stall insertion. So when we say stall insertion, we have to execute a delay first in order to wait for the read operation to finish, and then after that, that would be the time to execute the write operation. So we cannot perform it simultaneously. So we need to put on hold first the other operation, wait for the previous operation to perform, and then execute the stall insertion. And then once the operation is done, execute another operation. No? So in which delays the execution of the current instruction until the required operand is written to the register file. So we are delaying first the next instruction to perform while the other instruction is not yet finished. So that is what we call the stall insertion. So in short, we need to insert a delay between the interval of the two operations. So those are the different solutions on how we are going to undertake data dependency, since, of course, while pipeline tends to fast track the instruction process, but however, there are different concerns pertaining to that one, since, again, it provides a multitasking application, it provides an overlapping of instructions, so it is very difficult to manage those operations, and there are some other dependencies or concern along the way in the uh, execution of the pipeline operation. So currently, there are pipelining development, since the evolution of our computer architecture and organization is fast. So there are a lot already of researches and recent development in this pipelining operation. So these are the different pipelining developments. So we have the super pipelining. So it refers to dividing the pipeline into more steps. So if you can see, the basic stages of pipeline is only 5 stages. So to improve that one in a super pipelining development, so they add more steps or stages to provide a faster pipeline. So the stages in software pipelining includes the instruction fetch. So the instruction fetch is divided into two, the first half and second half. Then we have the register fetch, and then the instruction, another instruction execute. Then the data cache access is also divided into two. We have the first half and second half. Then the tag check and the write back. So if you try to look at this one, so we have 1, 2, 3, 4, 5, 6, 7, 8 stages. No? In a software pipelining, so they increase the pipeline into more steps in order to perform a more better multitasking application. Then we have also another one, the superscalar pipelining. So it involves multiple pipelines in parallel. So internal components of the processor are replicated so that it can launch multiple instructions in some or all of its pipeline stages. So both type of instruction shares two initial stages. We have the instruction fetch, and instruction dispatch before the fork or before the process. Often, however, superscalar pipelining refers to multiple copies of pipeline stages. So many of today's machines attempt to find 2 to 6 instructions that can execute in every pipeline stages. So in a super scalar pipelining, so they tend to provide a multiple copy of its stages. Let's say, for example, in a fetch instruction stage, they can replicate that one into 5 stages. So each stages can be replicated into more stages to give way to a better multiple operations, pipelines running in a parallel application. And then another one is the dynamic pipeline. So dynamic pipelines have the capability to schedule around stalls. A dynamic pipeline is divided into 3 units. So the instruction fetch, the decode unit, and then 5 to 10 execute or functional units, and a commit unit. No? So each execute unit has a reservation stations which act as buffers to hold the operations on the operand. So take note, in a dynamic pipeline, so they increase the execute functional units by providing a reservation station. So what is this reservation station? If ever that all of the tasks have already filled up in the instruction and decode unit, so they have what we call the reservation unit, wherein they can place here additional instructions as a reserve once the other instructions have finished, so they can accommodate still other instructions. Even though the instruction is currently full, they can have the reservation station to accommodate additional instructions, which is what we call dynamic. So when we say dynamic, once the instruction and fetch unit are free, so all of the reserved instruction will be moved again to the top and then accept another reservation for this one. No? So it makes more dynamic. It makes more a lot of units that can accommodate a lot of instructions simultaneously. All right, so to summarize our topic for pipelining, so we have the advantage and disadvantage of a pipeline operation. So again, the advantage is the cycle time of the processor is reduced, so in which it makes the central processing unit more perform better, no, and increase the efficiency of the output. It increases also the throughput of the system since the cycle time is reduced. So the lesser the time, the more output we produce. All right. So that is the advantage of a pipeline operation. And then it makes the system reliable. And by the way, before I forget, pipeline operations is only done in a RISC architecture, no? So a reduced instruction set architecture, we have the CISC and the RISC, right? So we're in the RISC, we are referring right now to our modern computers, right? While the disadvantage of these pipeline activities, of course, the design of a pipeline processor is complex and costly to manufacture. Yes, that is true since we are doing a multi-processing application. So that is why in our current computer systems right now, we have now the multi-core processor to manage synchronous, parallel, and multitasking operations. And the instruction latency is more, no? So of course, to resolve data redundancy, we need to have more latency. So the more latency that we have, it causes also more delays since this latency needs to have separate each processes, no? So the more stages we design, the more stages we add, the more latency also we add in between those stages, which may cause sometimes multiple delays on those simultaneous operations. And the instruction level parallelism is also called the pipelining or the ILP, no, which drives the performance. So parallel instruction implementation. So in here, we are breaking instruction into parts, as many as possible, that each part is independent and takes the same amount of time. So we have a balanced pipeline in such a machine. And the main limitations to perform are pipeline stalls. No? So to provide a parallel and simultaneous application, so in a pipeline environment, again, we break down instructions into pieces, no? to make it, to execute it in an overlapping implementation. So pipeline stalls have a number of sources, no? So to reduce the data dependency. Sometimes it may cause to have an insufficient hardware since due to the limitation or the expensive way of upgrading our hardware application. So it may take also long latency steps in the CPU or the memory. So the more stages that we have, the more latency it occurs. And sometimes it may cause missing information, as you can see a while ago in our example, wherein some of the branching operations may cause to jump to an incorrect ID that may cause incorrect or invalid operation. And of course, the removal or the mitigation of these stalls is still the major topic in an instruction set architecture. So that is why currently, no, there are still a lot of research how to improve the performance of our computer system, and it does not stop there. So every year we have a recent development. No, there is still a major topic, especially now that we are in a data warehousing, no, data management, wherein we are processing already a huge amount of data. So you have here what we call this quantum computing, wherein this is the new architecture right now in order to process a lot of data. Okay, so those advancement is still on our way, and along the way later on, we'll try how this computer architecture and organization evolved to have a more powerful and a better performance computing systems. Okay, so before I end again, let me share to you again this video.
There were 6 blind men who grew up in a village in India, and the community kept them safe and shared with them many stories. The men were curious about many of the stories they heard, but they were most curious about elephants. Based on the stories that each of them had heard, they argued about what elephants must be like. The community grew tired of these arguments and arranged for the men to visit the palace, where they were greeted by an old friend from their village who worked as a gardener on the palace grounds. Their friend led them to the courtyard. There stood an elephant.
I'm sorry, doctor.
The blind men stepped forward to touch the creature that was the subject
You can
of so
show
many
me
arguments. The first blind man reached out and touched the side of the huge animal. An elephant is smooth and solid like a wall,
or
he
subtitle
declared. It must be very
on
powerful.
this video.
The second blind man put his hand on the elephant's limb or trunk.
Yes, sir.
You can show me text or subtitle maybe on this video.
Is there any
No,
subtitles for this video, Mr.?
No, currently there is no subtitle since I use this one for YouTube. But however, I will try to discuss that later. It's all about the video.
Okay, thank you.
An elephant is like a giant snake, he announced. The third blind man felt the elephant's pointed tusk. I was right, he decided. This creature is as sharp and deadly as a spear. The fourth blind man touched one of the elephant's 4 legs. What we have here, he said, is an extremely large cow. The fifth blind man felt the elephant's giant ear. I believe an elephant is like a huge fan, or maybe a magic carpet that can fly over mountains and treetops, he said. The sixth blind man gave a tug on the elephant's coarse tail. Why, this is nothing more than a piece of old rope. Dangerous indeed, he scoffed. The gardener led his friends to the shade of a tree. Sit here and rest for the long journey home, he said. I will bring you some water to drink. While they waited, the 6 blind men talked about the elephant. An elephant is like a wall, said the first blind man. Surely we can finally agree on that. A wall? An elephant is a giant snake, answered the second blind man. It's a spear, I tell you, insisted the third blind man. I'm certain it's a giant cow, said the fourth blind man. Magic carpet, there's no doubt, said the fifth blind man. Don't you see, pleaded the sixth blind man, someone used a rope to trick us. Their argument continued, and their shouts grew louder and louder. Wall! Snake! Spear! Cow! Carpet! Rope! Stop shouting, called a very angry voice. It was the Raja, awakened from his nap by the noisy argument. How can each of you be so certain you are right? Asked the ruler. The 6 blind men considered the question, and then, knowing the Raja to be a very wise man, they decided to say nothing at all. The elephant is a very large animal, said the Raja kindly. Each man touched only one part. Perhaps if you put the parts together, you will see the truth. Now, let me finish my nap in peace.
Okay, so that video represents 6 blind men, no? So they are describing what an elephant is. So that is why they tried to let them touch and describe what an elephant is, but all of them have different description of what is an elephant. Okay, so similar to our computer system has also different parts, and we are not focusing only on the single component of that operation in order to define the power and the performance of our computer system. But however, if we try to combine all those parts and operations, so we can provide each component can contribute to the better performance of a computer system. So again, in behalf of Iloilo Science and Technology University, I would like to thank everyone. So I don't know if this is correct. Terima kasih banyak. No? A way of saying thank you for giving me this opportunity to share to you my topic, and of course to Dr. Mabacquiao and Dr. Badoles for providing us this opportunity to be part of the guest lecturer in the internationalization program of the university. So again, you can contact me through my social media account, Facebook, my YouTube, and my email if you have some other topics you need to consult. And by the way, I already share this file to Ari, and I believe that this was already uploaded to your learning management system. So again, I hope that I have shared you something pertaining to the pipelining topic, and thank you for this opportunity to be part of your university's lecture. So again, thank you and good morning.
Yeah, I will say thank you very much. Terima kasih banyak untuk for Dr. Ramil. Maybe I will re-explain to our students because maybe less than 50 students who are able to understand explaining using English.
Okay.
Yeah, I can maybe I speak bahasa. Jadi teman-teman, ya kita ucapkan terima kasih banyak kepada Dr. Ramil yang udah ngejelasin pipelining itu apa. Jadi kalau Dr. Ramil menganalogikan bahwa pipelining itu awalnya atau analoginya adalah di botol mineral ya, atau or mineral water, botol mineral water. Kalau saya analoginya yang udah saya jelasin di YouTube adalah analogi pipeline laundry ya. Jadi teman-teman kalau misalkan ada teman yang nyuci kan proses mencuci sampai dengan kering sampai dengan rapi itu kan dari mulai mencuci, mengeringkan sampai dengan setrika dan rapi gitu ya. Nah kalau misalkan Dr. Ramil tadi analoginya adalah dari mulai mengisi air ke botol, kemudian ya dari botol kosong diisi air, kemudian dikemas gitu ya. Jadi 3 proses itu kalau kita analogikan nggak semua akan membutuhkan proses lama ketika kita mau membeli beberapa botol minum gitu ya. Nah, dengan adanya pipeline ini akan menjadi lebih cepat ketika proses yang tadi seharusnya dari awal sampai dengan akhir itu beriringan dari awal sampai akhir. Nah, ini bisa dipercepat ketika tempat pengisian airnya kosong bisa diisi dengan botol kosong berikutnya gitu ya. Atau tadi ketika instruksi pertama sudah di decode, maka kita bisa mengambil instruksi yang kedua itu ya. Kemudian ya tak lepas dari analogi tersebut adalah adanya ketidaklancaran ya atau depending gitu ya, atau menimbulkan instruksinya tidak selalu cepat, tidak dicapai dengan cepat gitu ya, dengan kecepatan yang ideal. Tapi ya tadi Dr. Ramil bilang ada pipeline hazards gitu ya. Dari mulai struktural hazard, data hazard, control hazard. Nah ini pun hazard ini pun memberikan bantuan atau ya bisa mempercepat gitu ya, tetap bisa mempercepat. Bahkan di video yang pertama Dr. Ramil tayangkan, kita tuh ngetik di komputer itu bukan satu kali waktu gitu ya, bisa beberapa ratusan kata gitu ya, ribuan bahkan gitu ya. Bahkan selagi mengirim email itu kan kita bisa nonton video juga gitu ya. Nah itu kan prosesnya lama gitu ya, prosesnya banyak gitu, banyak instruksi yang kita lakukan pada komputer kita. Nah dengan adanya pipeline ini bisa mempercepat. Analogi lainnya adalah kalau misalkan di Muslim itu ada kalau mau sholat berjamaah di masjid ada tempat wudhunya gitu ya. Tempat wudhunya ada tempat wudhu cewek, tempat wudhu cowok. Nah kalau misalkan ratusan jamaah cowok gitu ya mau sholat, nah itu kan ada kita punya pipa-pipa air untuk wudhu gitu ya, untuk wudhu. Nah apakah 100 orang itu harus ngantri gitu ya di situ? Nah itu yang perlu kita lakukan, apakah hanya satu keran air atau hanya kita bisa menambahkan beberapa keran air. Bagaimana ketika ya mungkin tadi adanya hazard adalah contoh kasusnya ketika Jumatan, 100 orang ini mau Jumatan, ada tempat wudhu cowok, ada tempat wudhu cewek. Nah hazard inilah yang memberitahu bahwa sekarang mah hari Jumat, cowok pun boleh wudhu di di tempat wudhu cewek gitu. Ya karena udah memastikan bahwa memang di tempat wudhu cewek itu enggak ada ceweknya gitu, makanya jadi cowok pun masih bisa wudhu di tempat cewek gitu, karena sama-sama tempat wudhu ya, makanya bisa mempercepat pelaksanaan sholatnya gitu ya, jadi masuk ke masjidnya bisa lebih cepat. Nah gitu pun untuk komputer ya, atau di komputer. Nah, ada teknologi pipeline ini yang mempercepat ribuan instruksi yang memang kita instruksikan di komputer. Nah, bahkan di video terakhir atau saya nggak salah dengar tuh bahwa jangan khawatir, komputer-komputer di sekarang tuh ya pipeliningnya dengan tadi ada, bahkan Dr. Ramil menjelaskan bahwa pipeline sekarang di developnya udah enggak ya udah makin canggih lah gitu ya. Jadi dependency-nya, hal-hal yang menghambatnya itu sudah lebih teratasi. Atau nanti kita bisa pastikan juga ke Dr. Ramil, mungkin teman-teman juga ada yang mau ditanyakan, boleh nanti di chat disampaikan. Dan mungkin dari video yang terakhir adalah kita bisa nyimpulin, atau kita juga sering dengar bahwa ketika beberapa orang yang tidak bisa melihat dan belum tahu apa itu gajah, ya apa itu gajah, nah ya kan tadi ya tiap orang mempunyai pendapat yang berbeda, ya berbeda-beda. Sampai ujungnya ada orang yang menengahin ya, karena mereka berantem itu teguh dengan pendirian mereka ya, bahwa semuanya itu benar. Tapi kalau misalkan teman-teman yang buta itu tadi nurunin egonya untuk menyatukan semua informasinya, maka jadilah gajah itu gitu ya. Nah begitupun buat pertemuan kuliah sekarang gitu ya, teman-teman yang tadi menyimak apa yang disampaikan dengan bagus, dengan baik sama Dr. Ramil, pasti pemahamannya tentang pipelining itu berbeda-beda ya. Kan nanti di diskusi atau bahkan di sini bagi teman-teman yang mau menyampaikan kesimpulan, mau pakai bahasa Inggris silahkan, mau pakai bahasa Indonesia silahkan. Jadi kita mau menyatukan informasi tentang gajah itu apa, menyatukan informasi tentang pipelining itu apa gitu ya. Mau pakai bahasa Indonesia, mau pakai bahasa Inggris juga boleh. Atau silahkan jika ini ada dari Gilang ya. Nah, maybe that's our explaining for our student, doctor. And this we have one question for Gilang Bekti. Sir, permission to ask is a computer problem that often freezes or does not move? Is it because of the bad pipeline system in the computer, causing a delay in processing the input? Maybe you can answer this question.
Okay, so sometimes there are different um, problems that might encounter when our computer systems freeze now. So for example, it may be affected by number one, the amount of memory allocation that we use, no? And then if it is in a processor side, so most likely, especially when we're doing a lot of tasks, no? So we're performing multitasking. So sometimes our computer system has, especially if we have lower specification processors, so it might have the tendency to freeze since it cannot accommodate already all the instructions that is currently executing. No? So yes, that is true. It may be part of a pipeline operations wherein if you are executing already multiple instructions with the limited performance of your processor, so it may cause the computer to freeze or stop. So the solution in there is, of course, we need to free some of the process in order to resume the remaining processes. And it has an effect also on the hardware performance and the specifications of our computer systems.
Nah, itu Gilang, silahkan kalau misalkan mau menanggapi jawaban dari dokter. Kedengeran nggak, Gilang? Ya. Maybe thanks for the answer, Gilang said. And we have a second question. Sir, in our processor, we have cores and threads. Is it the same concept as pipelining? Maybe you can answer.
Come again, sir?
Yeah.
Can you read the question again?
Yeah. This question from Andi Dava. Andi Dava say, sir, in our processor we have cores and threads. Is it the same concept as pipelining?
Well, the concept of pipelining is more of how the instruction is being executed, and that is not on the hardware level. So we are under, so so pipelining is more of a computer architecture aspect. So when I say computer architecture aspect, it is more of execution of a specific instruction and how that instruction is being managed. So it is more on the logical part rather than the physical part of our computer system. So basically, the physical component just performs the operation, but the way how the instruction is being divided into multiple tasks and operations, so it is based on the architecture or the instruction set architecture of our computer system.
Gitu Andi Dava. Silahkan kalau mau menanggapi.
Yeah. Thank you, Mister. It's enough.
Okay. Yeah, thank you for the answer, Doctor. And the third question from Ayume Dina. Pardon me, sir. There's lack on the design of basic pipeline. Was function lack or just gap on there?
Come again, sir.
Yeah. On the design of basic pipelines, there's a lack or lex gitu ya. What's function lex? Just gap or what? Or just gap on there? Function of lex, lex.
The LUTs, no? So
Yeah.
referring to the LUTs. Yeah. So the LUTs is a register in between the two function. So it is just in there in between, no? So every instruction there is a latch in between. So in the design of the basic pipeline, that is essential, no? So it is really present. So the latch is really present. It's because that is where it divides or it separates the different stages through the number of latches. So the more instructions that we have, the more stages that we have, the more latches also that we are having. So it is still it stays there. So it is present always in between the two stages.
Okay, sir. Thank you.
Maybe the last question. I will. I just make sure.
Yes, sir. Yes, sir. You can ask question. Is Sir Ari disconnected?
I'm sorry, sir. I was connected. Maybe
okay.
maybe I ask one more time. Just just make sure in the work in the architecture.
Ini apaan sih anjing lagi gigan pakai undang-undang guru apa dosen luar.
I'm sorry, sir.
Yes, it's okay.
Pipeline applied in all architecture computer or just a few? Or today, today there are the others that don't use pipelining.
Yes. So pipelining is used in modern computers, no? So and especially now, our modern computers uses instruction pipelining so that it can perform multiple tasks or multitasking simultaneously. So it is currently in the computer architecture aspect wherein that is where they put the design into the processor to manage different computer at a different task. So if we are having a multi-core processor, so each processor has its own pipeline design also. So wherein if that multiple processor works simultaneously, so every instructions performed there in a pipeline operations of the computer processor. So currently, pipeline operation is part of the design of our modern computer systems.
Sure. Thank you for the answer. Maybe that's the last question. Uh, and for the next agenda is conclusion. Maybe the last uh, word you can say for this lecture. Take your time, doctor.
Okay, so
And
yes. So again, thank you very much for the time you spent, even though that we have some language barrier. So we thank you, Sir Ari, for interpreting my lecture so that the student can understand it completely. Since however, we do not stop there. No, this barrier could not stop us to deliver our knowledge to share to your students. No, and I'm very thankful for the students to attentively also listening to the topic and participate in the question and answer in order to clear their questions, and hopefully um, um, share you also the knowledge about pipelining and computer organization. So again, thank you very much. And I'm very thankful for this opportunity to be part of your learning experience.
and again,
Thank you.
Thank you.
yeah, we are all say thanks
Thank you, Kevin.
to uh, Dr. Remil. Yeah. Yes, because you prepared to spend your time as a guest lecturer in at Bina Insani University, and I hope this is not our last meeting, and we can meet again in other topics, maybe.
Yeah.
And uh, for the last agenda, we say thank and closure for these lecturers, and I will say thanks for uh, yeah, to Dr. Remil.
Can we open our camera so that we can take picture? Is it okay?
No, yeah,
Yes, sir.
okay. Yeah, ya,
We can
teman-teman
also
open kamera.
we can also see your beautiful faces. Right, so open your camera. Okay, so ready, 1, 2, 3, smile. Another one. So please, may I request others to open your camera.
Ya, ayo dibuka kameranya yang lain.
Okay, wait. Last one. Okay, so done, sir. Thank you very much.
Yes, I will say thanks to
Thank you, sir.
Thank you, sir.
Thank you.
You share.
Thank you, Chef.
Thank you, sir. Makasih, Pak Ari.
ya.
Okay, thank you very much.
Kasih banyak, Pak.
So, bye-bye. So are we ending the session right now, sir?
Yeah, yes. I'm sorry, doctor. Yeah, yes. This is end, and you can end or leave after this, I will send you a Google form to fill the attendance, and I will give you a certificate.
Yes, sir. So thank you very much again. So bye-bye. Thank you.
Ya, terima kasih teman-teman semua. Jadi itu pengalaman saya yang pertama pakai bahasa Inggris.
Ya Pak, makasih Pak.
Keren Pak, keren Pak.
Jarang-jarang Pak, jarang-jarang.
Ya, jadi ya saya aja bisa ya teman-teman, apalagi gitu ya belajar dari semester 2 pakai bahasa Inggris. Saya boro-boro semester 1 di S1 bahasa Arab ya, kan pusing dari Arab ke Inggris. Nah gitulah, tapi kemampuan orang gitu bisa semua bahasa gitu kalau mau belajar mah ya, tergantung teman-teman ya.
Pak udah.
Ya, ada komen nggak gimana tadi kuliahnya?
Mantep Pak, mantep.
Pusing Pak.
Lumayan
Rasanya, Pak.
bingung lah Pak.
Serap
Jadi,
semua Pak.
bagi yang bingung, nanti kan ada video ya. Ada video ulangnya, ada translate-nya. Nah, bisa ngulang-ulang lagi. Kalau yang nggak paham kalimatnya, nih kalau nggak percaya mah, ya saya share screen. Saya ngapain aja dari tadi itu Google Translate. Itu semuanya ya, apa-apa dibantu sama Google. Itu semangat buat semuanya. Jadi itu salah satu bagian dari perkuliahan kita arsitektur komputer. Untuk pipeline sebetulnya banyak juga sumber-sumber lain lah. Di YouTube ada yang mau bahasa Inggris, mau bahasa Indonesia, silahkan. Bukunya juga banyak. Pipeline ini seberapa penting. Terus di arsitektur komputer ini tadi Dr. Ramil bilang di komputer modern sekarang semuanya udah pakai pipeline, gitu ya. Kendala-kendala sudah semua teratasi. Gitu ya. Terus tadi juga ada beberapa pertanyaan yang memang kendalanya di kehidupan sehari-hari gitu ya. Itu aja. Terima kasih atas perhatiannya. Ya, pengalaman yang sangat berharga. Ya, kita akhiri aja dengan doa akhir majelis. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam.
Waalaikumsalam warahmatullahi
Terima kasih ya Pak.
wabarakatuh. Terima kasih Pak.
Terima kasih.